Okay, last optimization problem. Yay! This problem is going to deal with optimizing distance. So we have a graph of a function, and we want to know what point or points on the graph is closest to the given point. In this case, we have a graph of y equals 4 minus x squared, and we want to know which point or points on that parabola will be closest to the point 0, 2. There's the graph, and the point 0, 2 would be in here, and so we're just trying to determine which points on that parabola closest to that point. So we need our distance formula. D equals the square root of x1 minus x2 squared plus y1 minus y2 squared. Okay, we just need to know what our x1 and y1, x2, y2s are. Well, one of them is going to be the point, 0, 2. So we can go ahead and plug that in. It doesn't matter which one you plug that in for, x1 or x2, just keep the x and the y in the same position. So I'm just going to go ahead and plug it in. 0 minus x2 plus 2 minus y2. Okay, so now we need to know what is x2 and y2. Well, the only other option we have here is our function, because I can't pick a point on the graph because I don't know what point is already the closest. So I'm going to just use in general, because I need to know what is the x value and the y value of the point that will be closest. So I use this function to help me know that. So I'm just going to let x2 be x, and then y is going to be defined 4 minus x squared. Okay, so that's our y2, x2, y2. So I'm going to write that in here. So we have 0 minus x squared plus 2 minus 4 minus x squared squared. And that's our function. And I can clean it up, of course. So this is going to be negative x quantity squared, which is positive x squared, plus, and it's 2 minus 4, which is negative 2, minus negative x squared, so plus x squared, quantity squared. Now here's the, not really tricky thing, but just the special idea behind this particular one. This represents our distance, and that is in fact what we want to minimize. But the thing I know about square roots and radicals is that the bigger whatever it is that's under the square root symbol is, then the bigger the whole value of the square root will be. And what's smaller whenever the radicand's smaller, then the whole radical value itself will be smaller. So in order for me to minimize distance, I can actually get away with just minimizing what's under the radical, because if I make it the smallest it can be, then the radical will be the smallest it can be. Why do I want to do this? Because I don't want to take a derivative with that nasty square root in it if I can get away with it. I'd rather just take the derivative of this nice power function in here instead of something that's got the radical in it. So I'm going to sort of cheat a little bit and pull that inside part out and work with that. So I'm just going to call it D again, but I'm going to call it a big D this time just to separate it. It doesn't matter. There's nothing magic. That's just my own personal notation. So then I'm going to go ahead and multiply this out and clean up this function a little bit before I take the derivative. So this is going to be 4 minus 4x squared plus x to the 4th. That's that second piece, all multiplied out. All right, and then, so what I have is x to the 4th minus 3x squared plus 4. And that's representing my distance, but what it really is the distance up underneath the radical, okay? All right, now I can take the derivative of this. So d prime is 4x cubed minus 6x, and set that equal to 0 and solve. I'm going to pull out the common factors, so I'm going to pull out a 2x, and I'll have 2x squared minus 3. And so x will equal 0, and x will be plus or minus the square root of 3 over 2. Now I need to decide if all three of those points are closest to the point 0, 2, or if only one of them is, maybe two of them are. So I'm just going to do my sign chart. So negative square root of 3 over 2, comma 0, or not comma, but put 0 on there, and 3 over square root of 2. All right, so when x is very, very negative, negative a million, I'd have a negative value and then a positive value, so it would be negative, and so that value would be decreasing. When it's at positive a million, it will be positive, so over here it's going to be increasing. And then from negative square root of 3 over 2 to 0, then I'm going to have a small number, which would be negative, and so this 2x out in front would be negative, and then inside would also be negative. Negative times negative is a positive, so it's going to increase. And then on the other side, we're going to have a number between 0 and positive square root of 3 over 2. Then 2x will be positive, and what's in the parentheses, 2x squared minus 3, that would be negative, and so it's going to be decreasing. So what we see is that we have a max actually at 0 and a relative max, and then we have the mins are going to be at negative square root of 3 over 2 and positive square root of 3 over 2. And that's the distance that's being minimized there. So you would write your sentence, the points on the graph of y equals 4 minus x squared that are closest to 0, 2 are square root of 3 over 2, comma, 5 halves, and negative square root of 3 over 2, comma, 5 halves. And just in case you're unsure, I got the 5 halves by plugging the plus or minus square root of 3 over 2 back into the original function, because I'm looking for the points that are on that graph. So let me know if you have any questions. You'll work a couple of these problems tomorrow plus that worksheet, and we just need to review and make sure we got it all, and then we'll move on to the next topic. Thank you.